Hello everyone, Dennis here. In this video, we are going to discuss chapter 26, Earth and the Solar System. This video is brought to you by Ace with Dennis. Now, learning can be smart, not hard. Don't forget to subscribe and press the bell notification button to stop missing out free lessons. In this lesson, we are going to learn a few interesting topics, which are the Earth, Moon, and the Sun, orbital speed, solar system, the sun's gravitational field strength. Let's start the lesson with the planet that we are most familiar with, which is the Earth. The Earth is a rocky planet. It follows an elliptical orbit. It completes one full rotation on its axis once every 24 hours. It is tilted on its axis at an angle of 23.5 degrees. This line is the equator. The equator is the imaginary line that runs around the center of the Earth at 0 degree latitude. It splits the Earth into two parts, which are the northern hemisphere and the southern hemisphere. Day and night are created as the Earth rotates on its tilted axis. Half of the Earth's surface that is facing the Sun experiences day. The other half of the Earth's surface that is facing away from the Sun experiences night. Now, let's discuss the Earth orbits. The Earth orbits the Sun once in 365.25 days. As the Earth orbits around the Sun on tilted axis, it creates 4 seasons on Earth. When the Earth is at this location, it is on 20th of March. When the Earth is at this location, the date is on 21st of June. From 20th of March to 21st of June, the season is the spring. When the Earth is at this location, the date is on 23rd of September. From 21st of June to 23rd of September, the season is the summer. And when the Earth is at this location, the date is on 21st of December. From 23rd of September to 21st of December, the season is the autumn. And from 21st of December to 20th of March, it is the winter season. When the Earth orbits from A to B and to C, the northern hemisphere is tilted towards the Sun. Hence, daylight hours are longer than nighttime hours, and the northern hemisphere is having spring and summer. On the other hand, the southern hemisphere is tilted away the Sun. Hence, daylight hours are shorter than nighttime hours, and the southern hemisphere is having autumn and winter. When the Earth orbits from C to D and to A, the northern hemisphere is tilted away the Sun. Hence, daylight hours are shorter than nighttime hours, and the northern hemisphere is having autumn and winter. On the other hand, the southern hemisphere is tilted towards the Sun. Hence, daylight hours are longer than nighttime hours, and the southern hemisphere is having spring and summer. When the Earth is at B, summer solstice occurs, where the northern hemisphere has the longest day and the southern hemisphere has the shortest day. When the Earth is at D, winter solstice occurs, where the northern hemisphere has the shortest day and the southern hemisphere has the longest day. Now, how about A and C? When the Earth is at A and C, then night and day are equal in both hemispheres. They are called equinoxes where the sun appears directly above the equator. Now, let's discuss the moon. What is the moon? It is a satellite that orbits around the Earth. The moon travels around the Earth in a circular orbit. It takes about 1 month or about 27 days to complete orbiting the Earth. According to NASA, it takes 27.3 days to complete a revolution and 29.5 days to change from new moon to new moon. Both the Earth and the moon are moving around the sun. The moon revolves around its own axis in a month, which makes it to always has the same side facing the Earth. Also, the moon reflects light from the sun. It does not produce any light. Next, we talk about orbital speed. Planets revolve the sun following their own circular orbits. Similarly, satellites, example like the moon, revolve the planets following their own circular orbits. Hence, the total distance traveled by the planets and satellites equal to the circumference of the orbits, which is in circle shape. Therefore, we can calculate the total distance traveled in one revolution as 2 pi r. And we know that speed equals distance over time. Therefore, v equals to 2 pi r over t, where v is the average orbital speed in meters per second, r is the average radius of orbit in meters, and t is the orbital period in seconds, which means the time taken to complete one orbit. Now, let's look at one example about orbital speed. Given this diagram, which is the Earth, and there is a satellite orbiting around the Earth. A satellite moves in a circular orbit around the Earth. It is 580 kilometers above the surface of the Earth. The radius of the Earth is 6,400 kilometers. It takes 120 minutes for the satellite to complete one orbit. Calculate the orbital speed of the satellite in meters per second. Okay, so before we want to calculate the orbital speed, we need to know the radius first. So for this example, given that the radius of the Earth is 6,400 kilometers and the satellite is 580 kilometers above the Earth. Hence, the radius will be 6,400 plus 580, which gives us 6,980 kilometers, or change to meters, it will be 6,980,000 meters. The time given is 120 minutes, and we convert to seconds, which we multiply by 60, we get 7,200 seconds. So now we can calculate the orbital speed with the formula v equals to 2 pi r over t, and substitute the value 2 pi times 6,980,000 meters divided by time 7,200 seconds. Then we calculate the value, we get 6,991 meters per second. Next, let's discuss the solar system. The solar system consists of the Sun, 8 planets, dwarf planets, satellites, which can be natural or artificial, asteroids, and comets. First, the Sun. This is the Sun. It is a star, and it makes up more than 99% of the mass of the solar system. It is the center of our solar system, and its gravity holds the solar system together. Everything in the solar system revolves around it. Next, the 8 planets. You need to know the names of the 8 planets in proper order, starting from the planet that is the nearest to the Sun. And this planet is Mercury, followed by Venus, then the Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. All these 8 planets have their own gravitational field, and the gravitational field around planets is strong enough to pull in all nearby objects except natural satellites. 3. Dwarf planets. There are 5 recognized dwarf planets, which are Ceres, Pluto, Haumea, Makemake, and Eris. So why these planets are called dwarf planets, not the planets that we discussed in the previous page, is because the gravitational field around dwarf planets is not strong enough to pull in all nearby objects. As you may know, Pluto once is a planet, but then it was categorized as dwarf planets because of this reason. 4. Satellites. There are 2 types of satellites, which are natural and artificial. So what are satellites? Satellites orbit around a planet, and different planets have different number of satellites. For example, the Earth has only one natural satellite, which is the Moon, while Saturn has 146 non-natural satellites, and there may be more than 146, which haven't been discovered yet. How about artificial satellites? Artificial satellites are man-made. Currently, there are 9,494 active satellites in various Earth orbits. The last elements in solar systems are asteroids and comets. What are asteroids? Asteroids are small rocky objects orbiting the Sun. As you can see from the diagram, the asteroid belt lies between Mars and Jupiter. How about comets? Comets are frozen leftovers from the formation of the solar system composed of dust, rock, and ices. As a comet approaches the Sun, its ice melts and forms the comet's tail, which is a few 100,000 kilometers or longer. The next topic that we want to discuss is light speed. As we know, the speed of light when light travels in the space is 3 times 10 to the power 8 meters per second. So the distance between the Earth and the Sun is about 150.22 million kilometers. Let's calculate how long the time will the light to take to travel from the Sun to the Earth. So the distance between the Earth and the Sun given is 150.22 times 10 to the power 6 kilometers. We can represent it in meters and in standard form, which is 1.5022 times 10 to the power 11 meters. And the formula for speed is distance over the time. Hence, to calculate the time, we will take the distance divided by the speed. So for this case, the distance is 1.5022 times 10 to the power 11 divided by 3 times 10 to the power 8, and we get about 500 seconds, and we can convert it to minutes, which is 8 minutes and 21 seconds. So in other words, the Sun that we can see now in the sky is the Sun 8 minutes ago. So as distances in space are extremely long, we use light year to represent distance. 1 light year means the distance that the light travels in 1 year. So we can convert 1 light year to meters. So 1 light year is the speed of light times a year in second. So the speed of light is 3 times 10 to the power 8. A year in second will be 365 days times with 24 hours times with 60 minutes times with 60 seconds. And we'll get 9.46 times 10 to the power 15 meters. So 1 light year is very, very far. Let's look at one example about light speed. The radius of Saturn's orbit around the Sun is 1.45 billion kilometers. How long is the time for the light from the Sun to reach Saturn? Here is the solution. Given that the distance is 1.45 times 10 to the power 9 kilometers, we can represent it in meters and in standard form, which is 1.45 times 10 to the power 12 meters. So the time will be the distance divided by the speed. So for this case, the distance is 1.45 times 10 to the power 12, then divided by the speed of light, which is 3 times 10 to the power 8. When we calculate, we'll get 4,833 seconds, or convert to minutes, which is 80 minutes and 33 seconds, or we can convert to the hours, we get 1 hour, 20 minutes and 33 seconds. Alright, so this time is quite long, which means that the light travel from the Sun to Saturn will take about 1 hour and 20 minutes. Planets revolve around the Sun through circular orbits. As we have learned previously, we can calculate orbital speed using the formula v equals 2 pi r over t, where r is the radius of the orbit and t is the time taken for the planet to complete one revolution. Let's look at this example. The radius of the Earth orbit around the Sun is 150 million kilometers. Calculate the orbital speed of the Earth. So here's a solution. We know that the Earth will take 365 days to complete one revolution around the Sun. So we need to convert this time into seconds. So 365 days times with 24 hours times with 60 minutes and times with 60 seconds, and we'll get 3.1536 times 10 to the power 7 seconds. Applying the formula v equals 2 pi r over t and substitute the value, we get 2 pi times 150 times 10 to the power 6 times 10 to the power 3 divided by the time, 3.1536 times 10 to the power 7. Do note that the radius we have to convert into meters as well, hence we have to multiply 10 to the power 3 here. So we calculate everything, we'll get 29,900 meters per second rounded off to 3 significant figures. So this speed is actually very fast, which means the Earth orbits the Sun at this speed. Gravitational field strength. Gravity was discovered by none other than Sir Isaac Newton. He found out that all planets have strong gravitational field. They attract nearby masses with a strong gravitational force. Weight is the force acting on an object due to gravitational attraction. Due to weight, objects stay firmly on the ground and will always fall to the ground. Also, satellites keep orbiting planets. From the formula W equals mg, weight varies directly with gravitational field strength. When an object with mass is at different planets or satellites, for example the Moon, its weight will be different. This table shows the objects such as the Sun, some planets, and the Moon with their masses and gravitational field strength. These objects are arranged in descending order based on their masses. From this table, we can see that the greater the mass of the planet, the stronger its gravitational field strength. The stronger the gravitational field strength, the larger its attractive force towards the center of the planet. Hence, the mass of a planet determines the strength of its gravitational field. Let's compare two objects from this table. As we can see, the gravitational field strength on the Earth is greater than the Moon. The weight of an object on the Earth is greater than the weight of the same object on the Moon. Let's take an example. Here, when an object had a mass of 60 kilograms, then its weight on the Earth, WE, will be 60 times 9.8, which is 588 Newton, while its weight on the Moon, WM, will be equals 60 times 1.7, which is 102 Newtons. As we compare the results from these two calculations, we can see that it is much easier to lift a mass on the surface of the Moon compared to the same mass on the Earth. On the other hand, the gravitational field strength on the Jupiter is much greater than the Earth. The weight of an object on the Jupiter is greater than the weight of the same object on the Earth. Let's take a same example. When the mass is 60 kilograms, the weight on the Earth, WE, will be 60 times 9.8, which is 588 Newton, and its weight on the Jupiter, WJ, will be 60 times 24.7, which is 1482 Newtons. As you can see from comparing the results of these two calculations, we can make a conclusion that it is much difficult to lift a mass on the surface of the Jupiter compared to the same mass on the Earth. Gravitational field strength is almost constant on the surface of the planet, and it varies inversely with the distance from the planet. The further an object from the planet, the weaker force of attraction towards this object. So let's look at this diagram which illustrates this condition. So this is the Earth, and I have a green object with its gravitational field strength G1. And we have another red object which is further from the Earth and has a gravitational field strength of G2. From this diagram, we can conclude that G1 is greater than G2 as the green object is closer to the Earth than the red object. Next, let's look at the gravitational field strength of another very large object, which is gravitational attraction of the Sun. In the solar system, orbiting bodies are defined by what object they orbit around. Planets, comets, and asteroids orbit around the Sun. Natural satellites, for example the Moon, and artificial satellites orbit around other bodies except the Sun. A smaller body will orbit around a larger body. Gravity facilitates orbital motion by exerting a gravitational force that pulls the orbiting body towards the center of the larger celestial object. The larger body always exerts an attractive gravitational force on the orbiting object. Hence, the gravitational force always acts towards the center of the larger body. As you can see from this animation, the gravitational attraction of the Sun is what keeps an object in orbit around it, always pulling from the orbiting object towards the center of the Sun. This gravitational force will cause the body to move and maintain in a circular path. This animation shows how fast or how slow the planets orbiting the Sun. As you can see from this animation, the planets that are closer to the Sun orbit faster than the planets that are further from the Sun. Here is the reason. A centripetal force, which is the gravity, keeps the planets to continuously orbiting the Sun in a circular path. When the distance from the Sun increases, the strength of the Sun's gravitational field on the planet decreases, and the orbital speed of the planet decreases. The centripetal force is proportional to the orbital speed. The further away a planet from the Sun, the lower the orbital speed of the planet. As the orbital path for this kind of planet is longer and its orbital speed is lower compared to planets that are closer to the Sun, its orbital duration is also longer. Alright, now let's analyze the orbits of the planets with the Sun. This table shows all the planets in the solar system with their distance from the Sun in million kilometers, their orbital period, their density in kilograms per meter cube, their surface temperature in degrees Celsius, and their surface gravitational field strength in newtons per kg. They are arranged in the ascending order of the distance from the Sun in million kilometers. First, let's compare the distance from the Sun with the orbital period. As you can see from here, the orbital period is getting larger and larger when the distance from the Sun is getting bigger and bigger. Hence, the observation that we can see here is that the longer the distance from a planet from the Sun, the longer its orbital period. Mercury, which is closest to the Sun, has the shortest orbital period, which is 88 days, while the last planet is the Neptune, which is the furthest to the Sun, has the longest orbital period, and the period is 165 years. So here is the explanation why. The gravitational field of the Sun is weaker when the distance increases. The planets which are closer to the Sun travel faster than the planets that are further away from the Sun. Hence, they can complete their orbital cycle in a faster time. Next, let's compare the distance from the Sun and the densities of the planets. As you can see here, the planets that are closer to the Sun have higher densities. So our observation is planets that are closer to the Sun have higher densities compared to the planets which are farther from the Sun. Mercury, Venus, the Earth, Mars have densities about 4,000 to 5,000 kilograms per meter cube. On the other hand, Jupiter, Saturn, Uranus, Neptune have much lower densities, which are about 600 to 1,600 kilograms per meter cube. And here is the reason. Planets that are closer to the Sun are rocky planets, which have higher densities because they were formed in the hotter region during the early stage of solar system. The temperature was high enough to condense materials with higher boiling points, such as rocks and metal. Planets that are farther from the Sun are either gas planets, like Jupiter and Saturn, or ice planets, like Uranus and Neptune. They were formed in the colder regions during the early stage of solar system. The temperature was enough to condense materials with lower boiling points such as water and methane. Now let's compare the distance from the Sun with the surface temperature of the planets. As you can see here, the planets that are closer to the Sun have higher surface temperature compared to the planets that are further away from the Sun. So here's our observation. Planets that are closer to the Sun have higher surface temperature. Mercury, which is the closest planet to the Sun, has the highest surface temperature, which is 350 degrees Celsius. On the other hand, Neptune, which is the farthest planet to the Sun, has the lowest surface temperature, which is negative 220 degrees Celsius. And here is the explanation. Planets receive heat from the Sun by infrared radiation. Planets that are closer to the Sun receive higher amount of radiation from the Sun. Hence, their surface temperature is the highest compared to the planets that are further away from the Sun. And lastly, let's compare the distance from the Sun and the surface gravitational field strength. As you can observe from this table, the distance from the Sun does not have any relationship with surface gravitational field strength. For example, Venus, which is closer to the Sun, has similar surface gravitational field strength with Uranus. The Earth also has similar surface gravitational field strength with Saturn. Here is the reason. Surface gravitational field strength is determined by the mass and the radius of the planet. It can be calculated with the formula G equals Gm over r squared, where G is a constant, m is the mass, and r is the radius of the planet. Hence, the mass and the radius of the planet has the relationship with the surface gravitational field strength, but not the distance from the Sun. Alright, that's all for this video. Thanks for watching. Do you have any questions or doubts to ask? Feel free to write it down in the comment area. I would love to hear from you. Do you like this video? If yes, please don't forget to like it and share it with your friends. Until then, see you in the next video. Have a great day ahead.